Good morning. Today we're going to be looking at our Introduction to Proportions in our Interdisciplinary Math and Science unit with Living Environment and Algebra. My name is Mr. Cam. First off, just a review of place value. Reminder, ones, tens, hundreds, thousands. Thousands have 3 zeros. But as we get bigger, sometimes people forget that 100,000, that has 5 zeros because there's 100 and then another 1,000. Whereas millions have 6 zeros, and billions, when we get to billions, they have 9 zeros inside of them, 9. Just a little review because we are going to be working with some big numbers today. So just to start off, a basic reminder, you should have already learned this earlier in your algebra career, but a proportion is a part or share of something compared in relation to a whole. For example, a slice of pizza would be an example of a proportion because in this particular pizza, there's 8 slices, so 1/8 would be a proportion. Each slice is 1/8 of the pizza, so it's like a proportion or a part of the pizza. And it's always compared in relation to a whole. For instance, if we cut each of these slices in half, then each pizza would be 1/16 of a slice because now there's 16 slices. So it always depends on the whole and how many parts there are for the whole. Another example of a proportion might be a population. Like in Living Environment, you might have white rabbits and brown rabbits, and as they get eaten, there might be more of one kind or another, depending on whether or not they have a trait that is beneficial in that environment. In this case, the brown bunnies are more beneficial because they blend into the background, so their proportion becomes higher as time goes on. Another example of proportions is something you do every day, looking at different prices of different items to compare proportionally how expensive they are compared to one another. The reason we use proportions is because raw data is hard to see. If you look at this picture here, on the left side there's the raw data. It doesn't really make a lot of sense because the numbers are all jumbled up. Whereas on the right side we have a proportion where it's easy to see that half of them are this pinkish color and half of them are teal. Proportions help us to make order of disorder. Proportions help us to reason about the world. For example, if I said, 247 out of 494 students attended an assembly, those numbers don't really mean anything because it's hard to picture numbers when they're so abstract like that. Whereas if I just said half the school attended the assembly, that's pretty easy for us to understand because we know what half of something is because we've seen that in our lives. It has meaning for us and it's less abstract. So proportions take away the raw data and they try to show us what it is in the simplest form possible so that our brains can have a chance to understand it. They help us to see patterns rather than dealing with raw numbers. And proportions are created using ratios. Ratios are just basically a relation between two amounts. They're often represented as a fraction or as a percent. For instance, if there were 2 girls represented by the pinkish circles and there are 6 boys represented by this tealish color, the ratio would be 2 to 6, 2 girls to 6 boys. It could be written with a colon like it does on the left, or it could be written as a fraction, 2 over 6. However, remember that ratios are always relative. Relative means that it's always relative to whatever you're saying, because it could be different. Even the same thing, if we take the 2 boys and the 6 girls, if I say we want to compare the ratio of girls to total students, instead of 2 to 6, now it's 2 to 8, because there are a total of 8 students. There's 2 girls and 8 total. So even though it's the same exact situation, if it's worded differently, then the answer is different. Ratios can also be used when you're trying to compare things in science. For instance, in this picture, we're comparing chimpanzee hands to human hands. Although if you look at the thumbs here, the human thumb and the chimpanzee thumb, the sizes of the thumbs are very similar. They're not that different, but the size of the hand overall on a chimp is much bigger than a human. So even though our thumbs might be somewhat of a similar size, comparatively, our thumb is proportionally bigger than a chimpanzee's thumb because their fingers, their digits are much longer than ours, whereas ours are a little bit shorter. So therefore, our thumb to finger ratio our thumb is proportionally much bigger, which goes back to what you talked about with homologous structures in your living environment class. So we're going to do a few math problems today having to do with like a living environment context, but we're going to be doing particularly algebra proportion problems. So here's the first problem. It says if a human has 6 billion base pairs of DNA, that means they have 6 billion base pairs, and 2 people have 10% of their DNA base pairs that are similar, how many base pairs are similar? So if there are 6 billion of them, and 2 people have 10% that are exactly the same, how many are the same? In order to do this, first we have to calculate 10% of 6 billion. And the way you do that is you set up an equation. First you take 10%, and 10% is written as 10 over 100 because 10 divided by 100 is equal to basically 10%. So to find 10% of 6 billion, we have to put x over 6 billion because that unknown, that x, is the 10% that we're looking for. We'll just use 6 for right now because 6 billion is such a large number that it's kind of confusing to work with. So we're just going to work with 6 and then we'll convert it later. So for your first step, you should it should look as like x over 6, meaning x over 6 billion is equal to 10 over 100. And that is how we're going to figure out the answer to this problem. So what we're going to do here first is cross multiply. We're going to multiply the x times 100 and the 6 times 10. And when you multiply x times 100, you get 100x, and 6 times 10 is 60. Then what you're going to do is you're going to divide both sides by 100. Divide both sides by 100. And when you divide them both by 100, 60 divided by 100 is 0.6, so x equals 0.6. So we have to figure out what is 0.6 of 6 billion. And the way you do that is you do 0.6 divided by 6, gives you 0.1. And 0.1 times 6 billion is this number right here. Remember that if it has 6 zeros, it's millions. So this is 600 million. So for our final answer, we're going to say that if two things share 10% of their DNA, that means, and there's 6 billion total, that means that they share 600 million DNA base pairs. Try the second problem on your own. If a human has 6 billion base pairs of DNA, and two people share 25% of their DNA base pairs, and they're similar, how many base pairs are similar? So try and figure this out. You have 6 billion base pairs, and two people share 25% of them. How many do they share? Try and figure it out on your own before I go over it with you together. So in this particular problem, the way you would do it again is you would set it up as 25 over 100 because 25 divided by 100 is equal to 25%. Then you would put x over 6 billion again because we're trying to find what is 25% of 6 billion. So again, it's going to be x over 6 and 10 times 100, and we're going to cross multiply them. And so what we're going to do is x times 100 is 100x, and 6 times 25 is 150. So we're going to have 100x equals 150. And then again, we're going to divide both sides by 100. And x is going to equal, what is x going to equal? 150 divided by 100 is 1.5. So just like last time, since we're doing 6 billion, you would do 1.5 divided by 6 to represent the 6 billion, and the percent is 0.25. So we're going to multiply 0.25 times 6 billion, and when we multiply that out, it comes out to be 1.5 million if you do that on the calculator. So the answer for number 2 would be that they share 1.5 million DNA base pairs. And that's the end of today's lecture.